Hi, these are the notes for section 2.1, which is about graphing absolute value functions. So, if you remember back to your previous algebra course, you probably recall that the absolute value is essentially the distance that a number appears on the number line. So for example, if we have 0 here, we have 5, we have negative 5, the absolute value of 5, or the absolute value of negative 5, is the distance that number is from 0. So because it's defined as a distance, we know that that value is positive. That's one way we can think about an absolute value function. A more rigorous one is to think about it as something called a piecewise defined function. So the way we write a piecewise function is we write it with one of these curly brackets, and then we'll have what the function does for some part of its domain, and then what the function does for some other part of its domain. And you could have lots of different pieces, like this piecewise function just has 2 pieces. It has this piece and this piece, but you could have lots and lots and lots of pieces. So just to get a feel of how this works, if I want to do the absolute value of 5, well, 5 is greater than 0, so I do this. If I want to do the absolute value of negative 5, well, negative 5 is less than or equal to 0, so I do this. And we get that same effect. So again, you're probably already a little bit familiar with how the absolute value function itself works. But that's 2 definitions depending on what you've seen before, or what you're trying to do, or what you're trying to prove that could be useful. So thinking about it as like a distance on a number line, or as this piecewise function. This section, though, is about graphing absolute value functions. So before we talked about families of functions and parent functions, well, the set of all absolute value functions form a family of functions where y equals the absolute value of x is the parent function. And any absolute value function can be written as the form, let's just write it, y equals there. And you'll see these familiar a, b, h, and k. We know what these do in terms of a transformation. That was well covered in the previous module. If you don't remember that, I would encourage you to go back and look at your notes for section 1.3. So let's just take a quick look at the graph of the parent function, y equals x. And when I think about this, I'm going to think about this using the piecewise definition. So if I think about this, if I say pick some x's and some y's, this part of my piecewise function is a linear equation, just y equals x. So maybe I pick like 1 and 2. In that case, y becomes 1 and 2. And I bet I include 0. When I plug that in, I get 0. But remember, I'm going to put a little star here because 0 is not a member of that. That's actually moving into here. And then if I pick negative 1, that goes into there. But I still just have a linear function over here, right? This is still just a linear function, just y equals negative x. So the graph of my absolute value function is this V shape here, where you have 2 straight lines that are intersecting at this point. just like for quadratic functions, we call this point the vertex. And it turns out that, just like quadratic functions, the vertex is going to correspond to the values for h and k. Let's just take a moment and talk about the domain and range for this function y equals x, or I'm sorry, y equals absolute value of x. Well, if we start at negative infinity, we notice that tracks up to points, and any x values I choose are going to be represented as points in my function. So my domain is all real numbers. The range, though, if I start down here at negative infinity, there's no points on my graph that correspond to that y value. And as I move up, the first time that happens is here at 0. And I see that 0 is actually a y value on a point. And then any y value after that I choose corresponds to a point. So the range here is positive infinity, or I'm sorry, 0 inclusive to positive infinity. And then I notice here that if I reflect this across the y-axis here, this part of my graph gets reflected over here, and then this part of my graph would reflect over here. And so what I observe here is that a reflection across the y-axis is the same as the function itself, so I know that this is an even function. And that's going to hold for all absolute value functions. They're all going to be even functions. Their domains will all be the same, but their ranges could be different. So let's look at an example of just graphing something. Say let's graph, let's pick, say, g of x equals 4 absolute value x minus 5 minus 2. So there's a couple of different approaches. You could say, okay, well, for my absolute value of x, I know this contains the points negative 1, 1, 0, 0, and then 1, 1. And I could do a map just like we had done in the previous section. That would be okay. But that's a bit of overkill for what we really need to do here. So rather than doing that, what I'm going to do is just kind of make a little bit of an xy table. I'm going to pick some special values of x, and then find their corresponding values of y by just plugging them into the function. So although you could do that, like we had done before, I'm not going to do that now because it's a little bit more work than we need. So I'm going to pick 3 values of x. So to graph an absolute value function, one of those 3 values of x must correspond to the vertex. It actually has to be the middle point in my little xy table that I'm going to build here. So remember, before we said the vertex was this point h comma k. So here I see my h value is positive 5, and my k value is negative 2. Again, remember that because the general form has a subtraction symbol in it, if I plugged in positive 5, I would have the x minus 5 there. However, the k value has a plus sign in it, so if I plug in a negative 2, I have the minus 2 there. So just as a review, I'm sure all of you remembered that. Now, these remaining 2 x's, I can pick almost anything. So for this x to the left of the vertex, I just need to pick any value of x that's less than the vertex. So any number less than 5. So 4 would be okay, 3 would be fine, 2 would be fine, 1 would be fine, 0 would be fine, etc. For this point, I just need to pick a value that's bigger than the vertex. So 6 would be fine, 7, 8, 9. You'd pick decimals if you wanted, like 10.6. I don't know why you'd want to do that, but you could. So once I've chosen those values for x, I can find the value for y by just plugging back in to my function here. So g of 4 is 4 times 4 minus 5 minus 2. So again, the absolute values work like a parenthesis, so I'm going to do the stuff inside the absolute value first. And then the absolute value of negative 1 is just positive 1. And then 4 times 1 is 4, and minus 1 is 3. And here's a little hint, or a nice observation that we can make. You see how the difference between these x values is 1, and the difference between these x values is also 1? If we do that, if we pick our x values so that they have the same difference or distance from the vertex, the y values should be the same. So as long as I'm picking my x's in this careful manner, I get the other y value for free. Now, I claim that it's the same thing. You should be suspicious. So let's just demonstrate to you that it is the same, that this rule is going to hold. But we can see really quickly here that, what did I do? What did I do? Help if I did the right thing here. So, my apologies here, folks. I just was a negative 2. I copied a negative 1. So, copied the wrong thing. It happens. Don't shoot the messenger. Well, I mean, you can shoot the messenger, but be prepared for the messenger to shoot back. That's a joke. No one's going to shoot you. Okay. Similarly, we could describe the transformation here just like we did before. So we have an a value of 4. That means we have a vertical stretch by a factor of 4. We have an h value of 5. That means we're going to go right 5 units. And we have a k value of 2, negative 2. So we're going to go down 2 units. So if I were to graph this function, we had 1, 2, 3, 4, 5, 6. 1, 2, 1, 2. So we had 4, 2. We have 5, negative 2. And we have 6, 2. So here is our g of x. And if we wanted, we could compare that to the parent function, which is this here. Oops. Yeah, well, that there. And if you look at this, certainly we've been moved right 5 and down 1, or down 2. Just looking at the vertex. So like, whoop, whoop. And then there appears to be a vertical stretch because this one looks wider than this one. So this has gotten a little skinnier because it's been pulled up. So it's gotten tall and skinny. Okay. Also in this homework, you'll be asked to be able to go from a graph to a function. So let's say that we have the following graph. You know what? I'm just going to do this. So here's my absolute value function. So the key to doing this is still this form. So this will remind us very much like the quadratic, writing the quadratic model from the previous module. So I'm going to start, because I know the h and k, I know immediately that I can fill in the h and k. I know the h and k because the vertex is always h comma k. Since the vertex is labeled there, I can say that. Okay. Now, we have to make a little bit of assumptions here. So you notice here that unlike the quadratic one, I could have an A or I could have a B. What we're going to do is we're going to find two possible answers. So the first possible answer, we're going to assume that the B value is 1, and then find A. And after that, we're going to assume the A value is 1 and find A. So we'll get two possible answers for this. So let's go ahead and do that. So if we assume that the B is 1, we have this now, because the 1 over 1 just goes away. And to find A, well, all I need is another point off this function, like the point 0.03, and I can then plug that in and solve for A. So one answer I could write x minus 1 plus 6 would be this. Now, let's assume that A equals 1. So in this case, then we'd have g of x equals the value 1 over b, x minus 1 plus 6. I'm just going to do that to separate this. And we'll do the same thing. I'll plug in 0.3. When I do that, it simplifies down all the way to negative 3 equals, well, it's really the absolute value of 1 over b. But right away here, we know that this is nonsense. Why do we know that this is nonsense? Because remember, when we take the absolute value of something, the absolute value is describing the distance from 0. So that distance can never be a negative value. So this is like there's no solution to this equation. So the only answer we're going to report is this one. Is this sort of thing going to happen every single time? No, not necessarily. You could certainly have a situation where you can get an answer for both A and B, particularly if one of them is positive. That can certainly happen. Okay, the last thing I want to do is do an example where we use absolute values inside of a story problem. So what I'm looking at is example 3 from your textbook. This is on page 69. Stop laughing. So the situation, a little bit of background here. It says light travels in a straight line and can be modeled by a linear function. When light is reflected off a mirror, it travels in a straight line in a different direction. From physics, the angle at which the light ray comes in is equal to the angle at which it is reflected away. The angle of incidence is equal to the angle of reflection. So right here. You can use the absolute values function to model this situation. So let's look at an example. At a science museum exhibit, a beam of light originates at a point 10 feet off the floor. It is reflected off a mirror on the floor that is 15 feet from the wall the light originates from. How high off the floor on the opposite wall does the light hit if the other wall is 8.5 feet from the mirror? So this point here, we're going to just think about this kind of embedded inside of the xy axis. So I'm just going to kind of arbitrarily pick this as my y-axis and this as my x-axis. So in that case, this is the point 0, 10. This is the point 15, comma 0. And this is the point 15 plus 8.5 is 23.5, comma something. And this is what it is that we're looking for. Okay, well that doesn't seem so bad. What I'm going to do is I'm just going to write the equation for this absolute value function, and then I will use that absolute value function to solve for y. So this is my general form. Right away I know that the h and k from the vertex, and I'm going to assume that either the a or the b is 1. In this case, I'm just going to assume the b is 1. It doesn't really matter. I just picked one of them. I picked the b. So when I do that, I have a times x minus 15 plus 0, so I won't even bother to write it. So I'm going to now solve for a. I'm going to do that by plugging in my x and y coordinates. So I get 10 is equal to 15a. 0 minus 15 is negative 15, but the absolute value of that is positive 15. And when I divide both sides by 15, I get 2/3 is equal to a. Okay? So what I can say now is g of x equals 2/3 absolute value of x minus 15. So if I want to find g of 23.5, that's going to be 2/3 times 23.5 minus 15. And 23.5 minus 15 is 8.5. And 8.5, for the sake of argument, I'm going to just think of as a fraction, so I don't have to get out a calculator. That's 17 over 2. So those cancel out. So I end up with 17 over 3, or approximately 5.6 repeating feet off the ground. Everybody okay with that? I sure hope so, because you didn't have a choice. That is going to wrap up lesson 2.1, and thank you very much.